This is the last in a series of videos related to truth tables. This is a very simple application that actually came up by a man named Augustus De Morgan a few years back. It's kind of an interesting relationship between ANDed quantities and ORed quantities. Again, this is one that's very handy when you're doing logic in your program, but again, it's an operation that you will see in other courses if you take computer science and or engineering courses. So let's take a look at the first kind of De Morgan's law we have, and that is if we have a circumstance where we have a not, parentheses A or B, turns out that'll be the same thing as not A and not B. So let's take a look and see if we can prove that. Once again, we've had our 0, 0, 0, 1, 1, 0, 1, 1. In other words, we have covered all the possible bases of two quantities here, being the A and the B. So let's take a look at false and false. If we have a false or false, then neither one of them is true, so this will resolve to false. However, that will be inverted, and we will get a true out of that. Now if we take a look here, we have a not A, which is not false is true, and a not B, a not false is true there, so that will in fact be true, and in fact will resolve to true. Now let's take a look at the next one, a false and a true. Now this is going to be false or true. Now that, because at least one of them is true, that will resolve to true, but will be negated and become false. Again, we have a not false here, we'll get a true here, but we'll have a not true here, and we'll have a true and false. That will resolve to a false. If we come back over here with our true and false, you can probably see that it's going to be the same thing as the opposite false and true. I'm going to have a true here or false, making this expression true. Negating it will make it false. Here again I'll have a not true here, which will become false, and a not false, which will become true. I'll have a false and a true, and both of them are not true, so that's going to resolve to false. And finally, when I have true and true, both of these, true or true, will resolve to true, be negated, and become false. And if I have a not true and not true here, certainly that comes out as a false as well. So we kind of can show here through De Morgan's law with both a logical analysis and simply using the truth table as evidence to show that these two were equivalent. Now a little side note here for De Morgan's law. If you look at what happened here between these two, basically if I have a not on the outside, then all I did to translate it was to change the operator and not the two inside items. Let me repeat that. If I have a not on the outside, I changed the operator and I knotted the two inside items. We'll take a look at that again in just a moment, but it's kind of a handy little tool again when you're following some logic. Let's take a look at the alternative here. What if I have a not A and B? Is that equivalent to the not A or not B, which just basically flips our operators like we had them before? Let's take a look. If I have a false and a false, that's false and false becomes false. But flip that with a negate and becomes true. So we have that. And then if I have a not false or a not false, then I've got both of the items in an or, in fact, showing up true. Again, if I have a false and a true, that's a false and true will come out false and then be flipped and become true. And then, of course, if I have a false and a true, I'll have a true or a false, and at least one of those is true, so my or resolves to true. So I'll have the true there. And once again, it'll be the same thing for this group right here with the variables flipped. If I have an A, which is true, and a B, which is false, this resolves to false, negated, and it becomes true. If I have a not true here and a not false here, then at least one of these is true, and that will resolve to true when I have false or true. Finally, if I have both true, I'll have a true and true, but that'll be resolved to true, but I will flip that and it will become false. And if I have a not true here or a not true here, neither one of them is doing a true for me, so again that will resolve to a false. So we've shown again that De Morgan's law can translate here, and I'll again note here on the side, if I have a not on the outside, if I just flip or change from and to or and then put nots on the individual items, that is how I resolve De Morgan's law. It's a very simple strategy. You still need to prove it in a truth table or a logical circumstance, but it's not very difficult to do, especially with the truth table, because the truth table doesn't lie. It comes along and it says, all right, I've got an A is false, a B is false. What does that mean? I have a not A or not B. What does that mean? And so you can prove that with the truth table because it doesn't lie. Okay? So that will wrap up our group of videos on this system. The truth table is a very handy and powerful tool. Anytime you're going to set up a logical circumstance for your if statements, and later on for your looping circumstances, you really need to prove that your logic will work for every circumstance. And you will use that with the truth table to show that circumstance. So that will wrap up this video and our series.